which you're taking will be similar, right? Will be quite similar, right? Similar. That's the way we are taking out, right? Now here, what we do, suppose we are taking example of a ink we are taking. If you're taking the ink, we are putting it onto the chromatography paper and it dries, right? After that, we are putting a drop of water, right? When you're putting a drop of water, what happens? The drop of water spreads, right? Means that there's a solvent which you're having, right? The solvent spreads, right, over here, right? Now when the solvent is spreading, right, what do you see after this? The different components over here, the solutes which are quite similar to each other, right, they got separated, right? We have got a yellow over here, we have got the red over here, and we got the blue over here, right? So we can see from this graph, we saw from this paper, that the yellow component was the most soluble, and the blue component was the least soluble, right? So that's a very important portion we have to learn, right? That in this chromatography, we are trying to separate out different solutes from each other by their differential solubilities in the solvent, right? Isn't it? We are trying to separate them by the different solutes, by the different particular solubilities, right? Now going to this thing, next part is that if you see that the common way which we do it, what in the common way which we are doing that, suppose there can be two kinds of chromatography, right? Means basic stage, I'm telling you, right? That they will be a colored chromatography per solutes. They can be non-colored, right, chromatography solutes, right? So in this portion we are doing what? In this portion we are taking in the basic chromatography, we are taking a chromatography per paper, and we are putting a pencil line, and after that we are trying to put the all the suppose we are taking a mixture of the solutes over here, right? Now we are trying to assume that, okay, it contains A, assume that it contains B, assume that it contains C, assume that it contains D, right? Isn't it? We are putting it. After that, we are rolling it down and putting into the chromatography tank. When we put in the chromatography tank, what happens exactly? We are placing the solvent in such a way that this is just below this line, right? When we take this below this line, what happens? That the solvent tries to go up, right? Go up. Right? Solvent goes up. Now, when the solvent is going up, we are seeing what? The different solutes will be moving with the solvent, right? Based upon which is most soluble and on, right? Now, there's another parameter you have to understand, right? That ultimately what exactly happens? The main portion we have to understand that there will be two interactions. The solutes will be having two interaction. In the first interaction, we are seeing what? In the first interaction, we will be seeing that the solute will be interacting with the chromatography paper, right? Indeed. Guys, please try to message me, right? Which portions you want to go through, right? Please message me. I'll be going to the Born-Haber cycle today. And any other portions you want to go through, please message me quickly, right? Please message me, and please message in the Zoom chat also. We are taking this chromatography paper, and what happens over here? There will be an interaction with this chromatography paper, right? It will be interacting with this chromatography paper, right? This is called as the stationary phase, right? There will be a stationary phase, and the solvent which is moving up is a soluble phase, right? So this will be a resultant interaction which is happening, right? Now think of that. If the solute is more attracted, means there will be intermolecular force of attraction more with the stationary phase, right? With the stationary phase, right? So the solute will not go up fast, right? Isn't it? And if the solute will be having more intermolecular force of attraction with the moving phase or the mobile phase, it will be moving the most, right? Isn't it? So both the important thing you have to understand, that the affinity, right, or the intermolecular forces of attraction, that's very important for us to understand, right? The differential between the attraction, right, that will be leading to that one solid going higher, one solid going lower, right? Now, the next step of particular chromatography which we're doing, right? This is a basic part I'm doing, right? Is the non-colored substances, right? So if we take non-colored substances, right? When we take non-colored substances, what happens? You'll be seeing that whenever we are taking non-colored substances, right? The non-colored substances will not show up, right? We cannot identify it, right? Isn't it? See the example of the amino acids, right? In the amino acids, we have to see that we are taking that substance, right? We are taking that substance, and we are trying to put this. Now after rolling that, if after rolling that chromatography paper, what we are doing? We are putting into a solvent. Now remember one thing, there's a question which comes in a board, that if you are changing the particular chromatography paper, right, the movement will vary, definitely. It depends upon the intermolecular force of attraction which is there, right? If you're changing the solvent also, right, the intermolecular forces will be varying, right? So those solutes which will be having means they won't have any color, right? For those solutes we are doing what? After the chromatography is over, suppose the solvent moves up over here. After that we are trying to pick it up, and we are trying to spray neon hydrant over here, right? When you spray neon hydrant, right, you'll be seeing what? You'll be seeing that it will be showing up. Neon hydrant will be reacting with any amino acid, right? And they'll be giving you what? They'll be giving a violet color, right? So in this chromatography, we also know that ultimately we have to find out the RF value, right? This is the way we identify any unknown substance, right? By the RF value. Now, RF value depends upon what? If you see this RF values, right? This RF value will be depending particularly on what? The solvent which you have taken and the paper also. Because both will be interacting, right? Both will be interacting. The chromatography paper also will be interacting, and the individual solutes also will be interacting, right? Isn't it? So if you see the RF value will be what? Distance moved by the amino acids, right? And divided by the distance moved by the solvent. Now this RF value is a ratio. It will be adjusting in such a way that the ratio will be constant, right? This ratio will be constant. This is the thing we have to understand and master, right? The ratio will be constant. Now we are going to what? We are going into the portion of that what are the different kinds, right? For the different kinds we are of the chromatography we have to learn, right? Now, here the first thing we are to take what? The thin layer chromatography, right? In the thin layer chromatography, we have to make sure that which is the mobile phase, right? First thing, which is the mobile phase. Second, we have to ensure that what is the what's the stationary phase over here, right? In the thin layer chromatography, we are taking what? We are to take the filter paper which I showed to you, the filter paper which I use, right, in the traditional method of the chromatography. That is replaced by what? That is replaced by a glass, usually a glass, or a metal or a plastic sheet. Now that's not all, right? That will be coated with what? That will be coated, this thin layer of glass, that will be coated with what? They'll be coated with silica gel, right? Or we can take a alumina oxide, right? Al2O3. Now these will be acting as a stationary phase, right? Now, after this, when we see this TLC, what are the advantages of the TLC? The main advantage of the TLC is that it runs faster, right? It runs faster, right? Much faster. And most important, smaller amounts of the mixture can be easily separated out, right? Now, the spots are usually uh, spread out less, right? Isn't it? And the plates which you're taking, these are much more stronger, right? Much more rigid, right? Than the filter paper we are using. The filter paper will be absorbing the particular solvents, and there's a chance of breakage also, right? So this is very important, that whenever we are taking a colorless solute, right? Whenever we are taking a colorless solute, as I discussed to you, we can easily spray a locating agent, right? Now, the new improvised version is what? The new improvised way is that we can also shine ultraviolet light, right? Isn't it? This is also option. We don't use ultraviolet light for all solutes. We use ultraviolet lights for those particular solutes which will be having which will be absorbing the ultraviolet region, right? Isn't it? And there will be an emission spectrum happening, right? Means you'll be able to see the position of the solute, right, when the ultraviolet light is shown, right? Now RF value, we just did it. RF value is a ratio. This is a ratio. In this ratio, we are seeing what is the distance moved by the spot divided by the distance moved by the solvent, right? Now moving on to the next part, right? We see that if we see that the column chromatography, right? In this column chromatography, what exactly do we do? They're trying to use a powder, right? It's a solid, right? It's a solid. The stationary phase, if you take, right, the stationary phase is a solid, right? Usually we can take SiO2, right? We can take Al2O3, right? Or we can take any other substances which acts as a stationary phase. Is it clear to you guys? So stationary phase, you have to understand stationary phase and mobile phase. These two we have to specify. In this column chromatography, we are trying to use a powder, right? A solid powder, right? A solid powder. And we are taking this powder, right? And it is and we are trying to put it into a column, right? This column we're trying to put it out, right? And now what we're doing now, we are adding the solvent from the top of it, right? Isn't it? We are adding the solvent, right? This solvent is also called as a eluent, right? Do you get my point, right? Now if you see that the whenever we are trying to see this, right, that the components will be what, the components will be running with the solvent, we know that more soluble will be running faster, so it'll be coming down, right, it'll be coming down, right, like this, right. And we will be seeing what the extra particular solvent we are using can be collected, right, over here. Now the major advantage is what, the major advantage is that if you want to separate out a large proportion, right, a very large proportion of the solutes, right, isn't it? Fine. We can use this, right? Do you get my point, right? So this is very important, that if you see a column chromatography that uses a powder, and we are packing the powder in that particular column, and we are adding the solvent from the top, right? So this is called as a column chromatography, right? Now we come to the part of gas liquid chromatography, right? In this gas liquid chromatography, this is used by the detectives also, right? It's a very improvised version, right? It's actually one of the most ultra modern, right, things we are doing, right, the gas liquid chromatography, right. Here also you have to see that we are mainly taking what, we are mainly taking the phase, stationary phase, as a powder, right. We're taking a powder, which is coated with oil, right? Isn't it? Now, after that, we are doing what? Now, this is either coated. Now, you're going to take this. You're going to take this pipe over here. This pipe inside you can coat it, right? Inside you can coat it, or you can pack it also, right? You can pack it also. The stationary phase consists of powder, and we're taking a pipe, a capillary tube, a long capillary tube, right? Usually it will be around what? Usually it will be around 80 to 100 meters length, right? We're taking, and the diameter also should be specific, it's half millimeter, right, diameter we are taking, right. And we are going to take what, we are going to take this and put it into oven, right. Where the temperature can be also increased, right. Now we are coating the stationary phase inside this particular tube, right, over here, right. Now next part is that if you see that the mobile phase is what, this is the mobile phase, guys. You get to open your book. The mobile phase is the carrier gas. This is not a solvent. See, first time we are coming out of the solvent, right? In the earlier part, in the thin layer chromatography or in the column chromatography, we have taken a solvent, right, guys? We have taken a solvent. But see, this is the most ultra modern, right? It's the most ultra modern, and it can separate out very minute samples also, right? Suppose a crime scene has happened, right? In a crime, what happens? A minute amount of the substance is taken out, right? Isn't it? So we can use this. What we can use this in those situations where we can find out very minute amount of substances, right? Now over here we're taking a carrier gas, thus the moving phase or the mobile phase. Usually we are taking a unreactive gas. Usually it is nitrogen, right? That is more seen, right? We are taking but a nitrogen. Now in some more sophisticated way by which we can find out a minute one, helium is used, right? Helium gas is used, right? Indeed. Now these are the two, what, these are two the solvents which are using, right? Now next we are trying to inject the solvent we are inject the sample over here, right? Hmm. Now after we are trying to inject that particular substance over here, the solutes, different particular solutes, right? Now the sample will be carried by the gas, right? This is a solvent. This is a solvent. Oh, sorry. This is the mobile phase you're having. So more is the solubility of that substances of the solutes in this carrier gas. More faster will be going, right? Now you know what? This is connected to our what? This is connected to a mass spectrometer or infrared spectroscopy or NMR machine, right? This. So that's the reason you have to understand that this detector which you're having, right? This will be connected to mass spectrometry and parallel with the IR spectrometry and the NMR spectroscopy, right? So that's the thing we have to understand, that whenever we are taking a particular this gas liquid chromatography, right? This is very important for us to understand, right? That what happens over here, right? Hmm. So this is very important. Now moving on to the next part. See, okay, see. Now see, we have to understand that this thing we just did, right? That we are trying to connect the different particular IR or the mass spectrometer, right? Isn't it? So the different solutes will be leaving this column at different times, isn't it? Do you agree? What? Yeah, agree this thing, right? So obviously it will be depending upon what? It will be depending upon the solubility of that solutes in that particular mobile phase. The mobile phase is what? The mobile phase is will be the helium we are taking or the nitrogen we are taking, right? That's called the mobile phase, right? Isn't it? Now go to the next part, right? See, the time in which the solutes will be coming out, right, will be coming out, that will be called as the retention time switches, right? So various detectors you are trying to use, as I have told to you, right? So we can easily find out the type of the solute precisely, right, by adding a mass spectrometer or an infrared spectrometer or a NMR spectrometer, right? Isn't it? And most important thing is that this whole process, do you know what? This whole process is automated, right? Isn't it? Fine. So gas chromatography. Now open your book quickly. What are the advantages of this? It is extremely, as I've told you, right? This is used in the crime, right? The crime analysis, right? Wonderful machine. This is a most ultra modern part, right? It is used for, as I've told you, it is used to actually find out minute traces of the substances, right? Very minute traces of the substances, such as food stuff particular contamination, right? Even you even, you know what, you can also find out the suppose there's a uranium poisoning, right, in crime scenes, right? They try to find out that was uranium used to kill that person. But do you know what, uranium that is used in very small amounts, right? Isn't it? So this is very important, that if you see that every substances will be having a prefed retention time. Did you get my point, right? Every substance, this machine needs to be fed, right? The different solutes that should be fed with a retention time, right? Isn't it? So obviously when the substances is coming out, right, when the substance is actually coming out at a particular time, that time is a fixed for the substance, right? So to fit the data also, we have to fit all the datas of the retention times, right? And we can find out, right, that what exactly was the substances we have to take, right? Fine. Now coming to this part, we are coming to this part that the retention time, right? See, please open this book and try to underline over here, right? GC is extremely sensitive, right? This part, please underline over here. And this instruments of the component is coming out, right, can be directly fed to a mass spectrometer or an infrared spectrometer or an NMR spectrometer, right? Now you can underline this part also, the identification of the subs component, right, can be also matched by the MS, right? We can take the MS, right, mass spectrometer data, and also match it. Yeah, retention time also will be there. Now, when you are specifically attaching a mass spectrometer, right, with a GC, right, with a GC spectroscopy, right, is it? So this is called as the GCMC, right? It is GCMC chromatography, right? So in this GCMC, we are thinking what? When a gas liquid chromatography is actually attached with what? With attached with a mass spectrometer, right? So obviously, as the substance is coming out, we can find out the substances from the retention time. We can have an idea. Finally, to cross check it, finally to have a full idea about it, right? We can also attach a mass spectrometer over here, right? Got it? Is it clear? As the substances is coming out of the chromatography column, we note down the retention time, and the substances, it can be directly fed, automatically fed to the mass spectrometer, right? Isn't it? Now it's very very important, see, to know that who is carrying those particular solutes. Nitrogen is carrying, or helium is carrying. They are gases, right? They are non-reactive gases, right? So as they separate out the individual solutes, right, the individual solutes get separated, because the solubility of the solutes in this nitrogen or helium will differ, right? Isn't it? So this is a very important part, that the nitrogen or the helium can easily be heated, and the nitrogen and helium can go out, and the mass spectrometer will be only analyzing the solid which is there, right? Hmm. So you can open this book and mark this out. This is quite tricky part. See, now see, in this HPLC chromatography, what we are taking? We are taking high pressure liquid chromatography, right? Isn't it? High pressure liquid chromatography, right? As a high pressure liquid chromatography, we are taking what? We are taking the solvent, right? The mobile phase. We are taking the solvent, right? We're taking the solvent and we are using a pressure pump, right? A very high pressure pump, right? This is quite similar to what we've seen in the GC, right? In the GC, we did not pump the gas, right? The gas went on its own, right? We heated the coil only. So see, if you can see this, right? In the GC, we are taking that coil, that coil which is of 80 to 100 meters, and we are putting into oven. This is very important. Why putting in the oven? Because the rate of the reaction will be increasing, right? Isn't it? We are not putting a pump over here. In the high pressure liquid chromatography, what we are taking the solvent. Here we are taking a solvent, not a gas, right? And what we are doing, we are taking a pump over here, and after that we are injecting the sample, the mixture of the mixture of the particular solvent, sorry, sample, right, in this pipe, right? Isn't it? Now if you see that over here, right, the detector will be analyzing, right? As the solutes will be more soluble, right, that will be coming out first, right? Now remember one thing, you have to keep the pressure of the pressure pump as a control variable over here, right? We take the pressure pump as a control variable, we take the concentration of the solvent as a control variable, right? This two you have to compare, right? This thing, the pressure pump, right? The pressure of the pressure pump, right? And we are getting what? Will be getting that different solutes will be coming out at different times. So we have got that particular detector, right? We have got the detector, and the detector will be sensing the retention time, right? That how much time did that solute come out. A shorter retention times means what? Can everybody type in the message? Suppose a solute has got a shorter retention time, right? So is it having more attraction with the mobile phase or with the stationary phase? Can anybody type out that if the retention factor is smaller, right, means less time, right? It comes out faster. So is it soluble in the solvent more? Means in the mobile phase more, or in the stationary phase? Can you type out, guys? Hello? Yeah. Do you get my point? Did you get my point, Richard? Did you get my point? What I'm saying to you, Richard? Is it clear? Krishna, is it clear to you? Richard, can you say to me?
Yeah.
Can you understand this part? Krishna understood. Where are you not? It is clear, absolutely clear. I'm
Could you
asking that. I'm asking that the solute solute A came out the fastest, right? So what does it mean? The solute A was more soluble in the mobile phase or more soluble in the stationary phase? What do you think? Type out, everybody. I have got one answer only. Tiara, can you type out? Everybody type out. Richard, type out. Krishna, type out. This will be a easy cherry picking marks, right? Yes, right. Is it clear, Richard? You type out, please. Thank you. Thank you so much. Thank you so much. Krishna, if the solute A comes out faster, right? What can you tell? That it is more soluble in the mobile phase or in the stationary phase? Krishna? Krishna, tell me. Understand better. See, first you have to understand that when we have to do Born-Haber cycle, we have to know some important definitions, right? Isn't it? We have to memorize the definition. Otherwise, it won't be possible, right? The first definition we come across is standard enthalpy change of atomization, right? This thing we have to know, right? What is standard enthalpy of atomization? First thing we have to know, right? What is standard enthalpy of atomization? Standard enthalpy of atomization is the enthalpy change when 1 mole, right? 1 mole of the atoms, right? 1 mole of the atoms is formed from the elements, right? Isn't it? Elements. Under standard condition. 1 mole of the gaseous atoms. You have to remember this thing, right? Fine. 1 mole of the gaseous atoms. So I told you a trick earlier also that whenever we are taking 1 mole of the gaseous atoms, right, we are fixing 1 mole, right? 1 mole where we are fixing here. 1 mole of, suppose I'm writing the standard enthalpy of atomization for chlorine. How do you write? 1 mole of chlorine, right, is formed from its elements, right? Isn't it? Like this, right? Fine. We cannot change 1 mole. This is very important. 1 mole of the gaseous atoms of chlorine is formed from its elements. Elements is what? Chlorine. We have to connect the Rhine Brinkelhoff, right? We connect the Rhine Brinkelhoff. That bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, right? Right. We're connecting this, right? These are the diatomic molecules, right? Bromine stays as Br2. Iodine stays as I2. N stays as N2. Cl stays as Cl2, right? H stays as H2, right? O stays as O2. F stays as F2, right? So this is a diatomic. So these will be diatomic in the elemental state, right? So we cannot change 1 mole over here, right? We are forced to put half over here, right? So standard enthalpy of atomization is an endothermic process, right? Isn't it? And it will what? It will be plus 0.12, 1 to 1, whatever. Now we have to know the definition of what? We have to know the definition of the bond enthalpy, right? What is bond enthalpy? Bond enthalpy is the enthalpy change, right? Bond enthalpy is the enthalpy change when we break 1 mole of gaseous bonds, right? Isn't it? 1 mole of gaseous bonds is broken, right? See this, right? What is called as the bond enthalpy? When we break 1 mole of the gaseous bond, see Cl2 gaseous bonds breaks down to Cl plus Cl, right? Means one Cl2 gives you two Cl, right? Now this is also endothermic, so this is plus 242. Now, guys, can you tell me one thing? Suppose I'm asking Krishna. Krishna, can you tell me that as standard enthalpy of atomization is this, and bond enthalpy equation is this, right? This. Now, can you tell me over here, Krishna, that how are they interrelated? Atomization and bond enthalpy. Can you see how are they interrelated? For
Is that
diatomic molecules, only for diatomic molecules, not for all. Can you tell me?
how they're related? Did you
Yeah,
say?
how they related for diatomic molecules, guys. Note down this, right? Tier, is it clear? Tier, got a thing? What I'm trying to ask, that for diatomic molecules, right, Richard, right? Diatomic molecules, how they're interrelated? Can you tell me?
Uh,
Can anybody type it on the chat, please? Zoom chat. How are seeing that interrelation, right? Think. Can you check these two equations? You'll be telling, right? You'll be understanding this. Send me a Zoom chat. Wonderful, right? What about Tiara? Tiara, can you tell me that what is the relation you're getting? Tell me. If you divide this bond enthalpy by 2, you'll be getting this atomization, isn't it? See, isn't it? Wonderfully
yeah.
done, right? Wonderful. Wonderful. Yeah. Or you can tell that you can multiply this equation by 2, double, you can getting this. For diatomic molecules, this is a very crucial bit, right? We have to know this bit, right? Now, we have to now go to the part of what? We now go to the part of the ionization energy. What is ionization energy? Ionization energy is the enthalpy change when one electron, right? When one electron is removed from each atom, right? Isn't it? Is first ionization energy will what? It is the energy change when to remove 1 mole of electrons from 1 mole of gaseous atoms, right? Isn't it? We remove 1 mole of electrons from 1 mole of gaseous atoms, right? Isn't it? This is called as a first ionization energy, right? Now over here to remember one thing, the first ionization energy, right, is always and ionization is endothermic. Now you have to learn this part. Suppose I'm taking calcium. Calcium loses 2 electrons, isn't it? It loses 2 electrons, right? But does this lose this electrons in one go? It does not lose this electron in one go. You have to remember this, right? If you see calcium, calcium will be losing 2 electrons. But does this lose these 2 electrons in one go? It won't, right? It won't lose this electron in one go, right? Right? Why? Because first what happens? First, calcium will be losing 1 electron. Guys, this is very important. Did you get my point? The 2 electrons calcium should lose. Does it lose in one go? No, it does not, right? First, what happened? First, it loses 1 electron. Then again it loses another electron. Got it? Is it clear? This is called as the first ionization energy, right? And this is called as second ionization energy. Clear, everybody? What is the thing, right? So this is a very important point we have to master, right? When we talk about the ionization energy, right? If for that for those elements which are there in group number 2, there'll be two ionization energy, right? First ionization energy and second ionization energy, right? We are having, right? Right? Fine. Right. Now suppose electron affinity. What is the electron affinity? Electron affinity is in simple terms, you are putting an electron to an atom, right? We are putting an electron to atom. That's simple terms, is means that, right? We are putting an electron to an atom. That is electron affinity. Now remember one thing, that electron affinity definition is what? Electron affinity is the enthalpy change when 1 mole of the electrons is added to 1 mole of gaseous atoms, right? And we are getting X minus over here, right? Isn't it? We are getting this, right? Now, for molecules such as oxygen adds 2 electrons, right? We're getting O2 minus. It adds 2 electron, right? Did it? It adds 2 electron. Now, does this take in one shot on one bit? No, it does not, right? It won't take this electron in one shot. Is it clear, everybody? It won't take that electron in one shot, right? So, how does it take? It'll be taking stepwise, right? First, it takes 1 electron, right? Isn't it? Isn't it? Then it takes another electron. Is it clear, everybody, right? Isn't it clear to you? First, it takes 1 electron, then it takes another electron, right? Clear? This is clear to you. So this is very important for us to know that if you see that when we talk about when we talk about this, right, we can understand that When you're taking oxygen, it will be stepwise, right? It will be stepwise adding of the electron. So the first step is called as the first electron affinity. The second step is called as the second electron affinity. Is it clear to you guys? Understood this part? Fine. Now note down this important part. The first electron affinity for non-metals, right, is exothermic, right? This is exothermic, right? Suppose it is exothermic by suppose minus suppose 124. Suppose I'm giving a just a number. It's not actual number. The second electron affinity is endothermic, right? This endothermic. Suppose it is plus 198, right? Isn't it? Now remember one thing. This is crucial. Did you get my point? The first electron affinity for oxygen is exothermic. The second electron affinity for diatomic so non-metals will be endothermic. Now write down this: the first electron affinity and the second electron affinity, right, will be endothermic overall. This part bit you learned, right? Did you get my point? The first electron affinity and the second electron affinity will be endothermic overall, right? Isn't it? Fine. This bit you have to know, right? Clear, everybody? This is clear. Now we are moving on to the part. Now we're moving to the part of. Now we're trying to move on the part to the lattice enthalpy, right? What do you mean by lattice enthalpy? Lattice enthalpy is the enthalpy change, right? Lattice enthalpy is the enthalpy change, right? When one mole, right? When one mole of the ionic compound is broken apart into its gaseous ions, right? Clear, everybody, right? What is this? What is this part called lattice enthalpy? Lattice enthalpy is the enthalpy change. When one mole of the ionic compound, right, is broken apart into its constituent gaseous ions. Is it clear? Remember the definition, guys. Without it very difficult, right? What is lattice enthalpy? Lattice enthalpy is the enthalpy change when one mole of the ionic solid, right, ionic compound is broken apart, right, is broken apart into its gaseous ions, right? Clear? So this is very important for us to know that this is the thing we have to know, that the lattice enthalpy is the enthalpy change when one mole of the ionic compound is broken apart into its gaseous ions, right? This is very crucial, right? Fine. Is it clear? It's gaseous ions. And we have to learn now that the lattice enthalpy is always endothermic because you're breaking the giant ionic lattice structure also, right? We are breaking the giant lattice ionic structure also, right? That's very important, right? We're breaking down the giant lattice ionic structure, right? Do you get my point over here, right? So that's a very important bit you have to know, right, over here, right? Clear, everybody, right? So now going to the next part, we have to see that when we utter the word Born-Haber cycle, what exactly is a Born-Haber cycle, right? To understand the Born-Haber cycle, we have to know the definition of the enthalpy of formation, right? Enthalpy of formation, right? What is enthalpy of formation? Any guesses? Can you guide me, Snigdha? What is enthalpy for formation? I'll be asking Tiara next.
Is it the enthalpy change to form one mole of a substance from its elements in its standard states under standard conditions?
Uh, come again, please.
Oh, is it the enthalpy change to form one mole of a substance from its elements in its standard state under standard
Wonderful,
conditions?
wonderful. Yes, yes. What is enthalpy of formation? Enthalpy of formation is the enthalpy change when one mole of the compound, right, hmm, is formed from its elements, right, in its standard state under standard condition, right? See, sodium is the elemental state of sodium. What is chlorine? Does it come under Brinkelhoff? Yes, it comes under Brinkelhoff. So Cl2, right? Isn't it? Understood. Standard state of chlorine is what? Gas. Sodium is solid. So one mole, right? One mole of the ionic compound is formed from its elements in the standard state under standard condition, right? Isn't it clear to you, right? So we have put one over here. We cannot change one over here. I told you the trick. So we have to put half over here, right? Isn't it? Right. Now, you have to understand that enthalpy of formation is a single reaction we are writing, right? Is it a single step reaction? Is it a single step reaction? That if you mix sodium solid and it will be directly combining with Cl2 and giving you NaCl, no other things will be happening internally? Yes. No, it won't. It is not a single step reaction, right? Actually, what happens? First, sodium solid, right? Sodium solid has to be atomized, isn't it, guys? Isn't it? This bit is very important. First, sodium solid has to be atomized. Means you are getting sodium gas, right, over here, right? Gaseous atoms. Then after you're getting the gaseous atoms, means we cannot pull out the electron, right? We know that sodium has to lose an electron like this, right? GCSEs we learned, right? And chlorine has to gain one electron, right? And with this Cl minus and Na plus combines to give you NaCl. We know that, right? But actually, when you're pulling out an electron, or we are taking out an electron and adding electron, it has to be gaseous atoms. Fine. Ionization is what? Enthalpy change when 1 mole of electrons is taken out from 1 mole of gaseous atom. Remember that. So this is enthalpy of atomization. What we are doing. Second step is what? We are trying to pull out an electron. That is ionization energy. That is Na plus E we are getting. Now after this we are catching chlorine. See, chlorine is what? This is gaseous, right? But it is Cl dash Cl. We have to break the bonds. Means atomization. We have to convert to atoms, isn't it? We have to convert to atoms. We convert it to atoms. Cl gas, right? This atoms. This atomization of chlorine we are taking. Now after this, what happens? This electron which has popped out of sodium has to be put inside chlorine, giving Cl minus, right? This is what step? Electron affinity, right? Clear? This bit is clear. So that's a very important thing. We have to master that whenever we are taking this part, right? We have to know that this electron affinity, right? We are taking electron affinity over here, right? Next step. Now see, sodium ion and chlorine ion will be combining to give you what? NaCl solid, right? What is this step? This step is called as the, tell me, reverse lattice enthalpy, right? It's opposite of lattice enthalpy. We just this. That lattice enthalpy is the enthalpy change when 1 mole of the ionic solid is separated into the gaseous ions, right? See this, right? So this entire breaking down, what is Born-Haber cycle? Born-Haber cycle is very, very easy if you understand this thing. It is breaking down the formation of an ionic compound. See, it's a formation HF. Always remember that formation of the ionic compound is exothermic, right? Exothermic, it liberates heat, right? So breaking down of a formation of an ionic compound, right, into series of simpler steps. Can you see this? Series of simpler steps. This is called as Born-Haber cycle. What is Born-Haber cycle? Born-Haber cycle is the breaking down of a formation of an ionic compound into series of simpler steps, right? That is called as Born-Haber cycle, right? Now going to the next bit, right? We see that when we talk about this, right, we have to know another important thing, that if we see that when we write down the Born-Haber, you can take a screenshot already, right? When we write down the Born-Haber cycle, how do you write down the Born-Haber cycle? See, first what we do, first we are trying to take the help of the enthalpy of formation. It is exothermic, arrows will be coming down, right? We write down NaCl solid, 1 mole of the compound is formed from its elements, right? As she said, right? This is called the enthalpy of formation, right? Isn't it? Now, second thing is that if you see that we have to first convert this sodium solid to sodium ion gas, then you have to convert the chlorine diatomic molecule, right, covalent bonded, into chlorine minus gaseous ions. After we forming it, we can connect the lattice enthalpy, right? Lattice enthalpy is what? 1 mole of the ionic solid is separate out into its gaseous ions, right? That's the thing we have to cover, right? That's the thing we have to know, right? 1 mole of the ionic solid is divided into, is separate out into gaseous ions, right? Is it clear? Fine. Gaseous ions, right? So that's the thing we have to master over here, right? Is it? Fine. Now over here, we do what? We first connect this. See how do you connect this? We first connect this like this. I see. We are taking what? We are taking the enthalpy of formation. Is it exothermic? Yes, it's exothermic. So arrow pointing down. Now remember one thing, don't try to do both the things at the same time, right? Means don't touch chlorine and sodium. Don't touch chlorine now. Leave it now, right? First complete sodium. See what we have to do, Tiara, over here. We have to convert this into its gaseous atoms. First step. Is it clear, everybody? So this is enthalpy of atomization, right, of Na. Now after this endothermic, so arrow pointing up, right? Next is what? Next is that we are trying to take the sodium gaseous atoms, understood? And we have to ionize it, right? We are ionizing it, right? Fine. Na plus E, right? Isn't it? First ionization energy we are doing, right? We are ionizing it, right? Fine. After you are ionizing, we touch chlorine. See, we have to atomize it. So arrow goes up. This is up means endo. Arrow goes up, right? So it is up arrow. So enthalpy of atomization of chlorine, we atomize it, right? What is the enthalpy of atomization? 1 mole of the gaseous atoms is formed from its elements, right? It's obtained from its elements, right? Now the second step is what? We have to put this electron inside the chlorine, right? That is first electron affinity, right? Clear? This is called the first electron affinity, right? Arrow pointing down, isn't it? Arrow pointing down. Is it clear to you? Arrow pointing down. So that's a very important point we have to master, right? Arrow pointing down. First electron affinity of chlorine, right? Arrow pointing down. What we are getting? We are getting Na plus gas plus Cn minus gas, right? Is it clear, everybody, right? So arrow pointing down we are getting, right? Because it's exothermic, right? Now after, do not try to write down the lattice enthalpy first, because you don't know that where this will be ending, right? This line, right? So don't try to draw the lattice enthalpy first, otherwise you have to erase and you have to do my suggestion. Fine. After that, what we have to do, we are connecting with the lattice enthalpy over, right? Now, now we are doing what? See, this is process 5, suppose this is process 6. Now we have to put Hess's law now. See, we are putting a clock over here now, right? We're putting a clock. Now, when we are putting a clock over here, right? So the Hess's law tells what? All clockwises, right? All clockwises will be equal to all anti-clockwises. Write down this, please, huh? All clockwises, right? All clockwises will be equal to all anti-clockwises, right? Is it clear, everybody? Fine. All clockwises will be equal to all anti-clockwises. Now, tell me one thing. Eh, Uh, just 1 minute.